about how high-fidelity simulations of hydrogen combustion on supercomputers accelerate the energy transition.
Very good. Thank you for the nice introduction, and thank you for having me here to talk about some of our recent research progress that we made. And what you see here at the top is a turbulent hydrogen flame. And obviously that is what I call a high-fidelity simulation. It's done on a supercomputer. And what I'm going to talk about is some details on this one, but also how we can accelerate with HPC this problem of energy transition motivated by climate change. All right, before I start with the content, I would like to, first of all, thank some people. Hendrik and group leader at STFS and Driss both are here, contributed immensely to this talk, and also to Hannah. And for those of you who are German, you know, I do combustion. She just changed her name. She married, but that is, and I almost got the name wrong. So anyway, she helped a lot with some of the content, especially with the slides. So thanks to all of them. Now, they are part of a team, and I think research is a lot of team effort. And you could say, so this is the team simulation of reactive thermofluid systems at Darmstadt. But this team is really also part of a team. And when you look at the international collaborations we have, I consider the scientific community like a large team where we are like one team member. And being able to do all this research requires, and I would like to take this opportunity to thank them again, is tremendous support from both public funding bodies and industry partners that really allow us to do this exciting research. And I hope to excite you also a little bit about combustion research in the next couple of minutes. The way we do our research, and this is very much then reflected in what I'm going to talk about, is that you could say that our research dimensions or the research we're doing in reactive CFD, combustion CFD, really has 4 pillars. The first one is that we're looking at configurations that go from simple to complex. So we start to understand the physics in a very simple, for example, canonical flame, a counterflow configuration. Then we move to a laboratory flame, which is not like a technical combustor, but the insights we gain, how a flame structure looks like. This is then what we transfer to a technical combustion chamber here, for example, seen for an aero engine. We look at this for various energy carriers. And again, here it's mostly fuels that power a sustainable world. They can be solid, liquid, gaseous, and also metal. Metal, of course, is a solid, but can also become a liquid and gaseous in a flame. But today, I mostly talk about hydrogen as one of the most prominent energy carriers for future energy, you could say conversion, you could say transport for chemical industry. Hydrogen is a key component here. The way we do this is by computational methods, you could say from concept to convergence. And today I'll be mostly talking about HPC, quite obviously, if I go to a PAR CFD conference. But all this computing power does not help you if you don't understand the theory behind it, the physical understanding. And today, I mostly talk about direct numerical simulation and a little bit about large eddy simulation of reactive fluids. And this is what we're going to talk about. And then I thought, how do I structure this talk? And I think with the messages I want to carry or bring across, I really have 4 key messages and 4 parts of my talk. So the first one is, how has reactive CFD catalyzed combustion, coming both from fundamental research and up to product development. So you really look at real systems. Then I said, I want to talk about hydrogen. Then I probably need to answer, how can hydrogen help to fight or combat climate change? Why is it important for the energy transition? So that's the second part. The third part is then, well, we're facing almost disruptive change when it comes to computer hardware. So the question really is, how can the next generation hardware be exploited to answer the scientific questions we have? And this brings me then ultimately to my fourth key message is, how can HPC accelerate in a sense that time to solution or time to scientific discovery, hydrogen combustion. So these are the 4 things I want to talk about. And let me start with what has happened in reactive CFD. That's a little bit of a view back where we are and where we need to go. Now, reactive CFD you heard I also was in industry, but now I'm back for more than 14 years. I'm back to academia now. And now when you look at this, reactive CFD obviously is an important part of computational engineering in a broader scope. And for me, computational engineering consists of two parts. The first one is that I need physical understanding. That's a little bit of the engineering part. In terms of combustion, that means you need to understand how does a flame structure look like. For example, you have a thin layer, 100 micrometer thick only. How does the temperature evolve from, say, 300 Kelvin to 2000 Kelvin over an area or distance of 100 micrometers? How does species evolve? How are pollutants formed? All these things. So you need physical understanding to do this. And of course, you need the bridge to HPC. You need special numerics. And in the case of combustion, it's really you need numerics and HPC methods that can deal with multi-scale and multi-physics systems. And since probably many of you are more in the CFD, non-reactive CFD part, I'll try to explain a little bit what our challenges are in reactive CFD. And these are the challenges that bring these two things together. Now let's look at a real aero engine. That's an LES of an aero engine. One that is actually flying probably was not designed by CFD, but that's a Rolls-Royce BR710. And you see here an LES, that's not a DNS, obviously a LES of these temperature fluctuations. Now of these real systems meter size, you want to look at what are the scales involved in these systems. Now, let's look at the different scales at a temperature snapshot here. Now, when I look at the combustion part, and let's say that would be our LES grid, you look at flame thicknesses. So that's where the entire combustion physics take place. We say that's a flame thickness, and under these conditions, that's 100 micrometers or sometimes even smaller. Now you compare this to the fluid mechanics scales, and you know, in fluid mechanics and in turbulent flow, we usually say that the smallest scale we have are Kolmogorov scales. And what you find under technical conditions is that the Kolmogorov scales, are usually much larger, or at least larger than the flame thickness. So everything in terms of physics, what happens in a combustion scenario happens below the Kolmogorov scale. So in terms of resolution, when you go for a DNS of a turbulent combustion system, it's not sufficient to go to Kolmogorov scales, but bring another 7 to 10 grid points into the reaction zone. So that's why a combustion DNS and a typical fluid mechanic DNS has different restrictions. So keep that in mind. Now, but on the other end, this is not resolving from the, we are also, as a CFD person, you would be, well, say used to resolving in a DNS from Kolmogorov to the integral scale, but sometimes that's not enough. If you look at the, for example, thermoacoustics, then you get physical wavelengths that are beyond the integral scale. So these are sometimes also scales that you have to resolve. So in terms of multi-scales, combustion is really, I sometimes say it's so fascinating, sometimes it's also giving us a lot of headaches, but in terms of scale separation, that's quite a challenge. The second thing I would like to mention is multiple physics. Now, again, looking at the same case, obviously it's a turbulent flow, and you see here typical characteristics of a turbulent flow. You have a recirculation zone, you have vortex shedding, turbulent jets, flow separation and attachment. Close to walls, you have turbulent boundary layers. Sometimes you have effusion cooling, so there are active walls where you blow out cooling air. So these are more fluid dynamics problem. But then it's a multi-phase flow, so you have a spray. So you have to worry about breakup processes, droplet-droplet interaction, the fuel evaporates, and then at some point you actually enter the combustion part where you have flame stabilization, the flame might interact with the wall, and then you also form pollutants like soot, nitric oxides, unburned hydrocarbons, or CO. All of this needs to be captured in a CFD simulation, so that makes it multi-physics. And for many of these processes, you need separate models, and all of these models are closely linked to each other. So I hope that you agree that also multi-physics is something we really have to worry about in combustion research and getting this all in, and especially that introduces another multi-scale issue. For example, here the soot formation, these are nanoparticles. The smallest nanoparticles that you get here are around 1 to 2 nanometers, the first subparticles that you get. So this is also something you have to resolve. All right, now looking at how can you do this is, and I said this at the very beginning, you want to make sure that you have a systematic approach to deal with this. So we start with fundamentals, really basic research, really fundamentals where you understand in laboratory type flames, what is the turbulent flame structure? And then having learned a little bit about turbulent flame structures, you go in something that is application oriented. That might be a combustion chamber that operates under pressure, but you still have optical access. You can still see the flame. You go in with laser diagnostics and you can simulate this and you still can validate step by step your models, because in the end, if you go to industry relevant configurations like the one you've seen before, you cannot validate a model in such a configuration. You don't have the data to do this. You can evaluate whether the model is fit to do this, but you can not validate a model, right? So the validation part goes here. Here's more evaluation and looking if it can solve a practical issue. So this is really what you could say is an engineer's type of workflow where you go from simple to complex, looking at all these, you could say, unit problems, and all of this needs a unit test in a good software framework, then to handle all of these things. So this is where reactive CFD is, and that has been developed over decades. So this is not something one single person can do, but a lot of researchers, the entire community has been working on this, and now we're at a point where it has become an indispensable tool for both fundamental research and product development. It's a multi-scale and multi-physics process. In order to attack this, you need to go from simple to complex. And in our case, since we're not doing experiments, we're doing maybe numerical experiments, but we're doing computational work, we need HPC systems to solve that. And the HPC is relevant on all the levels. Even the most simple configuration requires an HPC system. Remember, when you're a fluid dynamics person, you do turbulence in a box, homogeneous isotropic turbulence. This is a classical HPC challenge. You always want to have the next bigger box. So HPC doesn't really relate to the complexity of the problem. It really is where you always push the boundaries. Well, the question is, all of that talk didn't say anything about the energy transition. So that's the next thing I have to explain a little bit where this becomes important. Now, the energy transition and the hydrogen part is my key message 2 and 4. So let me talk first about hydrogen and how does hydrogen help in the energy transition that we're, entering into now. So, and there are tons of numbers. There are tons of politicians giving you some insights on what needs to be done. We all have consensus of what needs to be done, reduce the use of fossil fuels, but there is no consensus on how we do this. There is, however, the International Energy Agency, which is widely accepted, and they put out numbers every year. This is called the World Energy Outlook. Now let's look at what they're saying. If you look at the so-called stated policy scenario, so this is what we already implemented to do. And you look at what is the energy composition in 2050. 2050 is the year where we want to be net zero. This is where we have net zero CO2. That's the big goal, right? In order to limit the temperature increase. So this is really what we do. And if you look at 2050, you see, don't want to go into all the details, but you see there's oil, there's natural gas, and there's coal. So these are fossil fuels. So this is one thing you want to get rid of if you want to combat climate change, right? So this is what we already do. Now, then there's the next scenario, which we call APS. That's not the American Physical Society, but it's the announced pledges scenario. So this is what we promised to do, okay? And even in this scenario, you see electricity goes up, the hydrogen appears, but there's still a lot of oil being in the system, and there's also natural gas, not zero. And then what we need to do in order to get to net zero is the NZE scenario, the most optimistic scenario. And you see there's a lot of hydrogen, there's still a little bit of oil, but in the end, if you sum everything up in this net zero emission scenario, and this is what many people have not realized, is that 40% of the energy is still provided by fuels. That might be carbon neutral, that might be carbon-free fuels. So it's quite clear that when you have these fuels, most of the fuels will be burned. So you could say in a nutshell that way beyond 30%, combustion, even in a net zero emission scenario, which is extremely optimistic, and I hope we reach it, about 40%, maybe 35%, of the energy provision worldwide will be related to combustion. Okay, so that's not something that will be a niche at some point. That's really of high economic relevance. And seeing that hydrogen and hydrogen-derived fuels are growing in here, it's very relevant to look at this. So that's why combustion is not going to phase out. Combustion is in fact becoming more and more relevant these days, because we're not now talking about improving a little bit of 1% efficiency. It's about designing systems in a disruptive change to work with hydrogen. So it's really about, you know, that's an engineer's dream. You could start with a white piece of paper and you can do everything new. And one example is a hydrogen-powered engines until 2035. That's the promise that Airbus did. So 2035, we're going to fly with hydrogen. And this was just launched a couple of years back. And there's also a roadmap in between. And so when we started working with Rolls-Royce on these systems a couple of years back, we didn't even know whether we burned the hydrogen pre-mixed or non-pre-mixed. So it's really, you start with a white piece of paper and you know in 15 years we have to fly. Okay, so again, that's what I tell my students. That's an engineer's dream. It's not about talking to some guys and say, we always did it in this way and that's why we don't want to change. Here, the change is disruptive and that's where the engineers are needed. Okay, so when you say hydrogen, well, the first question, everybody had basic chemistry. You could say hydrogen is the smallest molecule. That's where you start with the hydrogen, the periodic table of elements. So you go to H plus H is H2. So that should be a simple fuel. And the chemistry, in fact, is not so complex compared to other fuels. But hydrogen is highly reactive. You know this from your basic chemistry class, maybe. And we usually measure this in a laminar burning velocity. That's the front speed of a flame that moves through a stagnant medium. You would have a pre-mixed mixture. And you compare this to methane. And here, that's how much fuel to air you have. One means stoichiometric conditions. Here you have more fuel, you have less fuel than needed. And you see here, for methane, the basic ingredient of natural gas, you have limited flammability limits and a fairly slow flame. You see hydrogen. That basically burns all over the place. Whatever you mix, it burns. And it burns very fast. And it comes also with some safety implications on explosibility and things like this. So it's very highly reactive and it's highly diffusive. For an engineer that ever designed a sealing, the most challenging sealing that you can get is for hydrogen, because it's a small molecule. It can always go anywhere. So this high diffusivity also has a drawback, and some of you have been in this mini symposium before, that these lean premixed hydrogen flames feature what we call thermodiffusive instabilities, because they're so diffusive. And I come back to this later. And what that means is you mix hydrogen and air in one cell, you ignite it in the middle, a laminar flame develops, and this laminar flame breaks up. So this is not a turbulent flame. This is a laminar flame that by itself is unstable and creates more surface area. And I'll talk about this a little later, where this comes from, about curvatures in these flames. I'll skip it at this point. But what I want to say is that this is not everything that creates curvature in more surface area. Usually you say turbulence creates more surface area. Here, the laminar and the turbulent part creates more surface area. And you could say, now you take, for example, a hydrogen flame and a methane flame, you tune them to have the same burning velocity, you put them to a turbulent flow. What you see is that in the end, the flame length of the hydrogen flame is shorter, which means it burns faster. So there's also something that you cannot learn from the mixture, how it reacts to turbulence. So now the hydrogen is also in a turbulent flame much, much faster than a methane flame. And the reason is these thermodiffusive instabilities that I just showed you, and they, in fact, appear also in realistic systems or real systems. And this is an example. It's probably hard to see if you haven't seen it 100 times, but this is an internal combustion engine, optically accessible. You see the cylinder head, you see the ports, you see the piston. And in this engine, optically accessible, we can look at the flame front, and this is from our Partner Institute, RSM, Andreas Dreitzler in Darmstadt, and they have visualization of a turbulent flame inside an engine. And so this is the flame propagating from the top towards the piston. And what you look at, when you look closely at these flame fronts, you can see the thermodiffusive instability under high pressure, high temperature conditions. So this is not something that appears in just a little bit of a laboratory academic setup. It really happens in real flames. And so this is something we have to worry about. So the problem is that all current combustion models basically neglect this effect. So that is an issue. And that's why we have so many hydrogen projects at the moment. So in order to understand this, you need HPC, because then you can look, and this is something from Aachen, where they looked at different fuel-air equivalence ratios. They looked at different pressures. They looked at different temperatures. Where does it appear? And you see sometimes it's more pronounced, sometimes it's less pronounced of these thermodiffusive instabilities. So obviously there is an effect of many, many parameters, and you need to understand this. So HPC is the way for scientific discovery here, because you need to understand what happens under technically relevant conditions, and you need HPC to explore this. You cannot do an experiment for this. You don't have the 3D unsteady resolution that you need for this. And the only way you can do this is by high performance computing. Then you can build models. And if you would compare a case where you neglect these thermodiffusive instabilities, then you would get a flame that looks like this, very long. You include the physics now, and you see the flame is much shorter. So obviously, this is the way we need to go. The Lewis 1 approximation, which means that the heat diffuses with the same speed as the hydrogen, and this is what we usually assume in hydrocarbon flames, that would fail miserably for hydrogen. So all the models that we developed over decades for hydrocarbon flames, I wouldn't say useless, but they can be considered a good starting point. But it's also in model development, we're looking at almost disruptive changes where what we did over decades is not working for this fuel anymore. So the question is, how do these interactions scale to real condition? And this is again where exascale HPC will provide answers, and I'll come to the exascale aspect in a couple of minutes. All right, so that tries to answer the second part. Hydrogen, can it help in the energy transition? Well, hydrogen is a key enabler in the energy transition. The challenge, or maybe the good news for this, it's so different that we have probably a decade work ahead of us. So the combustion characteristics are very different from conventional fuels. So it's really something we need to do, and it's really where the scientific community has to provide models that can be used at some point when a company designs an aero engine, an internal combustion engine, a household burner. You know that we're building gas turbines in Germany, hydrogen ready, but the systems are not hydrogen ready yet. That's why we are entering research collaborations right now. Not because we don't understand how hydrogen burns, but what about flashback? I'll show you one example how flashback can look like. So there are many, many things in reliability and safety that we need to address when it comes to hydrogen. Because hydrogen is highly dynamic, all the hydrogen flows are intrinsically three-dimensional because the instabilities are three-dimensional, and you don't even have to go to turbulence. Even the laminar flames are three-dimensional. And we have a basic understanding of the underlying phenomena, which is good. So we do have a physical understanding. We are not able to predict it under realistic conditions at the moment, where you cannot do DNS. If I can do DNS and I have a code to do it, I wouldn't say it's a plug and play, but you still have to worry about terabytes and terabytes of data. But we're not even there yet. So we're really, that's what makes it so exciting, at least for me, that I do something where we can explore something new almost every day. So the question is, how can HPC and the next generation of hardware contribute to answer these questions? And so what I want to talk about a little bit is how does aspects like heterogeneous computing, GPU acceleration, maybe even green computing come into play? And you know, exascale, we're at the right place. You know, we'll have an exascale computer in Jülich very soon. So the question is, what do we do with all this computing power? I do have an idea, and that's what I want to talk about. Now, before I do this, I want to give you one outsider's view, because, you know, I'm a little bit older. And, you know, I started out, when I did CFD, I started out being on proprietary Unix systems. You know, I did a system administration on HPUX systems, you know, all these different Unix variants. Then there was, and they all had their own processors, something you probably cannot imagine these days now. So HP, SGI, Sun, they all developed their own microprocessors. They had their own Unix, their own microprocessors, their own compilers. Then Unix came along, BSD as well, but Unix came along. I started with kernel 1.6, I think. So that's, you can imagine how old I am. But so then everything became a shift. So we went away from these RISC-based systems to CISC, and that was commodity hardware. So we could benefit as an HPC community from commodity hardware. We now had an operating system that can operate it. We had compilers that can operate on these CISC systems. Then they can stream extensions, vector things, all into play now. And as you all know, we're entering the next phase of disruptive change. And the other one was not disruptive. Now the next one is disruptive with GPUs. But you know, you can think about what other disciplines can say, okay, I see all this computing power makes sense. And when you look at CGI, so computer-generated imagery, so some of you might recognize some of the movies, but you just look at how special effects developed over the years. So this is how special effects looked like in the 60s. Actually, I didn't see that. So the 70s, so looks not so fancy. 80s, the first time you see rendering, volume rendering and all that stuff. So Jurassic Park, I just watched with my kids. They still love that. See all these movies. So this is how computing power helped as well. Lord of the Rings here. This obviously doesn't carry across under these light conditions. Star Wars, that's important for me. I think this was day after tomorrow, but and Marvel, of course, I have the pleasure to watch with my kids as well. So all of this shows you how computing is not just for HPC. I mean, we have to take the position, we benefit a lot from HPC. And, you know, when a lot of these things were all SGI made, you know, Pixar was probably the biggest operator of SGI machines at some point because they had the graphics card. Now we're back thinking about how do I use GPU or graphic card accelerators for CFD. So keeping that in mind, let us look from a CPU perspective a little bit about how much computing power do we actually have. Now, let's look at the #1 in the top 500 list over the years. So this is how it develops, and you see the flops here, 18 exascale and petaflops, how that developed over the years. And you see here the Frontier 2022, already the fastest computer already back then. So this is how it developed. And obviously this is exponential growth, or at least here you see the logarithmic scales. Now, interestingly enough, that's not all. Let's look over 30 years. That was the numerical wind tunnel here. That was over 30 years, how many orders of magnitude we crossed in this time. Now, I would like to enlarge this picture a little bit with video game consoles, because these are now having a lot of floating power. And of course, this is not entirely correct because it's also GPU sometimes. But stay with me for a second. And you see here that the PlayStation 5 2020, well, I mean, this is about the shift you have from the fastest computer, the ASCII Red, in '98, okay? You can even go further and put in smartphones. And this is the computing power of an iPhone 15. And when you look at this and try to make, if you want to give someone who's not an HPC expert, you want to give them a very short answer how we benefit from computing power, you can actually say that it takes about 30 years that you carry the power in your pocket that did not fit in the bus before, okay? So this is the amount of things that we can use with the computing power that we get. And that's a picture I stole here, but that's a Craze 2 supercomputer in Apple iPhone 4. You see that's how much it takes. Now, obviously things have changed, and it's not so easy anymore to use all of this. Let's look at Frontier here, and the top #1 here in the numerical wind tunnel here, 140 cores, a couple more here nowadays, 1.2 exaflops. So that's quite a development. You see here, that's always the top one. this is the sum of all the top 500. So the top one you already see makes, well, it's always sort of the hero system. It's not just one among many, it's just the hero system. And if you look at the top 5 nowadays, except for the number 4, you see all of them are basically using accelerators, AMD, Intel, NVIDIA, AMD. So, so it's quite clear that things are changing. So computing power exascale means new hardware. And the question is, does that matter to us? And so 4 out of 5 of the current top 5 HPC systems have GPU accelerators. And you can look a little bit closer and look at even more. If you look at the top 500, how many of these do have accelerators? And you see this is a very clear trend. As of now, in the current top 500 list, 192 use accelerators. And so that the hardware means it's getting increasingly complex, it's heterogeneous, we have new memory system and hierarchies, everything is implemented, but then do our codes work on these systems, right? So that's the big question. And then the question would be, what do we need? And from a CFD perspective, you can always ask, how did develop over the years the flops over network latency, flops over memory latency, flops over network bandwidth, and flops versus memory bandwidth? Well, being in a CFD, you know, this is really the number that is, for us, the most relevant one. We say memory bound, et cetera, et cetera. But unfortunately, this is the one that also has the smallest increase. So we don't benefit as much as we could. That's the storyline here. So we probably have to think about, with these disruptive changes, do we need to do something different? And another thing that we shouldn't forget here is you look at hardware specifications and what is now for NVIDIA or AMD, let's look at something, what they have in terms of GPU here. So we are, as a CFD community, very much used to say, I do everything in double precision. Okay, that's a long time ago. When, you know, again, I'm very old, and you know, we have for a long time, we had 64-bit processors with the register to take that, and very long time ago, we had 32 bits, but now everything is 64. We could do this, and now the problem, however, is that the new hardware is not made for this. So the floating point that you can get on the double, well, it's much larger when you just go to single, or you go even to half. That's something I've never seen in my CFD, but, well, you trade it in for floating point operations, okay? So relying on the notion that we always need to do double becomes an issue. For the other machines, it was not an issue because the hardware was designed to do it. That's not the case anymore. So we have more low precision performance, and this is why, because this special hardware for matrix operations is driven by machine learning. So we don't have that. So, so current hardware development is driven by machine learning, artificial intelligence. What we need usually is high memory bandwidth, high floating point with 8-byte performance, or at least 32 or 4-byte, high memory capacity, and a fast interconnect. What the hardware provides to us is single precision hardware, and they drive GPU accelerated hardware. And this is really in a contradiction. So this is not what we need. So the question is, do we rely on the old hardware? Do we say we don't change anything? Or is it really up to us that we say the future CFD code should be suited for single precision, at least partially? We need to develop them for modern GPU accelerated hardware. And we probably need to optimize the relation between flops and memory bandwidths. That's probably what we need to do. And that is not just a single rewrite of a few lines of code after profiling. Well, so when you look at what we do have is legacy codes, because multi-scale, multi-physics, that's not something you write on an afternoon because you're bored, right? So there are decades of development in these legacy codes, widely adopted by the scientific community, large multi-purpose codes, and in Europe, well-established codes that have been run. And some of them are ported to GPUs, but mostly it's CPU-based. And these are just some of them. The new codes are mostly would be developed from scratch, optimized for current computing, supercomputing hardware. And the two ones that we're looking in the framework of numeric combustion is NEC-RS with the plugin for CRF, for the combustion part and the Pellet combustion suite that you see here. And I'll just spend a little bit of time on NEC. And so that's it's the flow solver, it's spectral element code, complex geometries. Don't want to go into all the details here, but you already see where we're going. It's matrix-free operators evaluation. It has a lot to do with storage and work. It's a low Mach number solver. And for the reactive flow plugin, we have optimized kernels in order to go for the stiff chemistry systems, because I didn't talk about this, but the chemistry is also stiff. The Jacobian, the eigenvalues are very far apart. And that means that you have to have special ODE solvers for this. Developed over many years, now needed to be ported to GPU systems. Some aspects more, a custom GMRS solver that takes account of FP32 or so, 4-byte precision and overlap MPI communication. But so if you want to know more about this, there's a mini symposium over the next 2 days. And you see here the talks that you see, and you're highly invited to come and look at these interesting talks here. So it's called Computational Fluid Dynamics with High Order Spectral Element Methods based on GPUs. So and obviously, we're looking not exclusively, but a lot of that is looking at combustion and how we bring in combustion. Now, please join us this if you want to know more about this. Now, the third message, how can next generation hardware be exploited? I'd say, well, it will drastically change reactive CFD. It's almost disruptive. I don't use that very often, but I'd say for us, it's disruptive. The systems are shifting strongly to GPU. So if you want to do bleeding edge combustion research, you probably want to conduct this on a bleeding edge novel system, you need a new code. You could say legacy codes are best ported to GPU architectures. New codes are developed and optimized specifically for novel computing architectures. We will still keep the other things because, again, you don't do this in an afternoon. Multi-physics, multi-scale with decades of experience will still be there, and we will have CPU systems, but we will have a shift, and that takes time. And I think it's to acknowledge that this time we need to start right away, or we have started. Now, the last thing I want to talk about is a little bit about how we can now, with all what I talked about, accelerate H2 combustion research. And in the end, I want to give you a little bit more of a couple of examples where we are standing and what kind of physics we need to resolve by this. Now, again, I showed you my simple to complex animation. You see, we start out with fundamentals where we understand how does a flame stabilize. Then we go to an application-oriented, pressurized, for example, combustion chamber with optical access. We look at pollutant formation, for example, or how this effusion cooling, cooling air blows out here, interacts with the flame that comes down. And then finally, we go to an industry-relevant configuration. Now, thinking about how would that look like, I probably didn't see that, but there was a slight animation. Now we have a hydrogen edition of that workflow. And then obviously we don't have CO, we don't have soot, but we have other things to worry about. So we have to understand the laminar flames first, which we're still not we have not fully achieved yet. We have to understand how turbulent flames then behave. How does that in linear instability interact with the turbulent flame? And then we need to go to industry relevant applications, and I'll talk about flashback under high pressure, which is relevant for safety operations. And then in the end, you wonder about how does diffusion come into play, how does a flame curvature come into play, and how does strain imposed by a turbulent flow change the hydrogen flame structure. Things that were not so relevant in hydrocarbon flames become now extremely relevant for hydrogen. And I'll just walk you through a couple of examples. Let me just double check my time. Okay, I'm good. No, I'm speeding up. So that's the DNS of the spherical flame that you saw. And why is that flame faster or getting these instabilities? The heat that the flame basically gives to the unburned mixture. So here's unburned, here's burned. This is the flame. So you have a lot of hydrogen here that diffuses extremely fast to this flame. And the heat, which is high, the temperature is high here, is slow getting here. That means that if you have such a flame here that is concave, that is getting slower because the hydrogen does not reach it. And here it gets faster, and that after some time leads to this here acceleration and deceleration of the flame. So this is what happens in these flames. You bring this in, you want to build a model. So you don't want to do DNS. You look at the temperature, the hydroxyl profile, or the hydrogen consumption, and you bring in one of the models we developed for hydrocarbon flames, do the hydrogen addition of that, and you look at the error in temperature, hydroxyl radical, or the consumption rate of hydrogen. You see there are lots of errors in these particular regions, and then you figure out that you have to include the local curvature of the flame in the model. If you do this, you get a much better result. So this would be the improved model with curvature, much better. Now, then let's get this one to a turbulent flame, and you see here turbulent flame, slot flame. We look at this. It's an HPC application running on 20,000 cores. You look at this flame, that was the one on my top slide. Same thing, temperature, hydroxyl radical, and the consumption rate. You bring in the old model, obviously large errors. You bring in the improved model, still large errors. And then you understand that in the turbulent flame, things have changed again, and you have to bring in the strain imposed by the turbulent flow. If you do this, then, well, obviously this is not our model is perfect, but this is just the beamer. But there's still a little bit of discrepancy, but much smaller than before. So it's a qualitative statement I can make here. So, but it's much better. So you have to really build understanding step by step how the model must be built. So more complex physics increase the size of the manifold. That's a little bit of a technical term here, but that needs more resources. I'll skip over this for time. This is running on 60,000 cores, and where we want to look at flame wall interaction, but same story here is that you do a DNS of a fairly simple configuration. These were run in Norway. I'll skip all this for time, but what I want to slightly spend on some time is a DNS of a simplified configuration we do. That's a so-called McKenna burner, and you see here that you have a jet, you have a pilot, and you have a co-flow, and you have a turbulent flame in here. Now, we did these with both with OpenFOAM and NextCRF, same conditions. Now let's do, let's skip how we do the boundary conditions. Now let's look at what does a legacy code and what does a new code do on the same case, all right? So with OpenFOAM, we ran that on 64 million cells, 40 micrometer resolution, 2,500 cores, and that was a time to solution about 18 days, okay? So that was, I think, in Munich. So the NextCRF, we have two resolutions with one, and that's a spectral element code, so you cannot compare them one by one. But here's seventh order in space, so 145K or 2.5 million. And then you had different resources here. And then you could approximately say this one and this one is slightly comparable, but then the time to solution is drastically reduced. So you have a code that can make use of this new hardware. And those of you who have done this, they will be surprised how fast you can get an answer if you have a code that can do it. Developing these codes is not a piece of cake. It takes some time, and sometimes you bug chasing for months. But we're getting there, and it's very, very promising. So last example that I want to give is flashback. Flashback is something where you have a mixture coming up here. You have a central bluff body. The flame is supposed to burn here, but unfortunately, sometimes it burns back. That's what we call flashback. Very bad. If it happens once, the system is gone. So that is never supposed to happen. If it happens, that looks like this because the metals here are not fit for the temperatures of a flame. So they just melt. This is something you want to avoid. Avoiding means that you have to design a system that doesn't have flashback. That requires physical understanding what is happening. And this is one thing we ran that was in Munich, trying to understand these on 20,000 cores. That's a couple of years old now. But then you really see this creeping of the flame along the bluff body or the central body. And then you can understand what kind of fluid dynamics in front of the flame allow the flame to actually go down. So this is an HPC thing, very difficult to do in experiment. And that opens up the next one. And this is really hot off the press. That is what we call almost realistic configuration from DLR. And where we want to understand also flashback into this pipe here. And what you can see here, you want to go to higher pressures. And now we do what we call a conservative estimate. And this, however, will become feasible on Jupiter. So the exascale run these cases under pressure. And this is quite a number of breakpoints. But so the exascale GPU systems now will also allow us not just scientific discovery, but also go to more realistic conditions, right? So we can also make an impact on, at some point, technology development. So I would like to summarize this part then. And I have a few slides, but then I'll stop. So combustion, how has RCV catalyzed combustion? Well, combustion is a multi-scale, multi-physics process. And HEC allows us to follow a path from simple to complex, build understanding, and do scientific discovery. Hydrogen will be the key puzzle in the successful energy transition. Well, the combustion characteristics are difficult to master, and that's where we need HPC and the next generation of hardware. And for this, we need to be on the novel, the bleeding edge systems, if you want to say. And for this, we need also new codes developed and optimized specifically for novel supercomputing architectures. And then we can also go for scientific discovery. This is usually the thing we'll mostly do. We want to understand the physics with HPC. But for the first time ever, we can really now also use supercomputing to bridge the gap between fundamental and applied sciences, because we can actually bring the DNS into technically relevant conditions. Now, this is a unique chance we have for the next 10 years. Not only do the scientific discovery part, but also bridging the gap to something that was unattainable a couple of years back. Well, these were the messages. I just want to briefly share a few things, what another exciting things are on the market. So I talked about hydrogen. Another thing we're doing is metal fuels. So we burn metals. Sounds very exotic. We know this, however, for a long time, because if you look at the Ariane 5, the booster rockets, they burn metals because they have high energy density. If you do fireworks, that also is a metal burning. You know, maybe know this from the basic chemistry class, that the metals give you certain light emissions. Now, we can now use metal powders as recyclable, zero carbon, high energy density carrier of renewable energy. You burn this like you would use coal or biomass. You take powder of metal and burn them in a flame. That's an experiment in Darmstadt. That's a simulation from my group. Really trying to understand this one now as it becomes more available. Now, and the most exciting part of that is that you don't burn them in air, but they are so reactive you can burn them in water. Now, that sounds even more exotic, but what really happens is that you can take a metal, bring it into contact with high temperature steam, you oxidize the metal, you get a metal oxide. Iron oxide is something similar to rust. It's also a powder, and then you get hydrogen and heat. So you have a reactor, you bring metal powder and water, let it react under high temperature conditions, so a couple of thousand Kelvin. You get hydrogen, high temperature steam, and heat, and you can use that in a variety of applications. So this is something that takes a lot of momentum nowadays. And I'm particularly looking at aluminum in this particular context. The DRC thought it's also valuable to fund this. And so we look at aluminum steam combustion for clean energy. And why do I tell you this? Because this is another example of multiple scales, multiple physics. And let me show you why. So you burn in a reactor steam and green aluminum. And what I want to look at is here the turbulent flame. What I get out of this is heat and green hydrogen. That's one way of producing green hydrogen if you do the green aluminum with renewable energy. And then you can do this for electricity generation or for chemicals, because this is where we need the H2 as well. You don't want to burn it always. You also need it for chemical industry. Now, you want to look at the reactor. That's a meter size problem, okay? But then you zoom in and then you're back on a millimeter scale. So you see a metal air flame or metal steam flame with micrometer sized particles. So then you're already made 3 orders of magnitude. The powder is micrometer. You look at the powder itself or one particle, you see 2 non-miscible liquids. You see attached flames, detached flame, nanoparticle formation. So a lot of physics happening, but that happens on the micrometer scale. And then you go to the nanoparticles that here formed. Obviously, this is nanoparticles that you have to worry about. And then you have to connect all this information to predict again, the reactor. So the dynamics on the nanometer scale govern what happens on the meter scale. So this is really the challenge, and this is why we need HPC, because we need, again, a systematic approach to bring all of this in a simulation of this reactor. And this, so we're not running out of ideas where to use the HPC resources for. Okay, so that was probably the last thing I want to say. These are my 4 key messages. Thanks for being here. Happy to answer any questions, and I hope you realize that combustion is not up for good. It's actually one of the key things to realize the energy transition. Thank you.